It's easy to get yourself stuck on life's big questions. Should I travel the world or settle down and have a family? Should I take that high paying job or try my hand at being an artist? Should I get combo number 1 with the burrito or combo number 2 with the taco? And of course, I know what you're all thinking. The big one, right? The one question that keeps us all of us engineers at least, up at night pacing the floor, racking our brains. Yeah, that one, Diodes or multi-layer varistors. Sorry. I should have warned you before I just blurted it out, but there it is. We've got to face these difficult things sometime, and now is as good a time as any. Hi, I'm Amelia Dalton, host of Chalk Talk, and today we're taking on the biggest of life's questions. How should I protect my circuit? With diodes or with multi-layer varistors? Luckily, I have an expert right here with me today, Dean Beckley from AVX, and we're going to straighten this issue out once and for all. And before we get started, don't forget to click that link. There you can find out more information about diodes or multi-layer varistors from AVX. Hi, Dean. Thank you so much for joining me today.
It's nice to be here.
So a lot of designs require circuit protection, but there are a bunch of options and most of us don't know what the best option is for our application. Dean, what should we consider?
Well, most designers will use either diodes or multi-layer varistors, and that typically is the big decision that has to be made up front. For years and years, engineers have been designing with diodes. Multi-layer varistors are relatively recent development in the late 80s. Some of the engineers' concerns are that maybe the diodes will fail open mode while the MLVs will fail as short circuits. And if they fail as a short circuit, the designers are really concerned as well as their companies because it can result in burning or failure of the circuit. The other concern that has recently come up has been size reduction, particularly on the circuit boards. And engineers are now finding that they don't have rooms for these great big diodes anymore. And that is one of the design features of the MLVs that offer size reduction. So, what do I do when I design my circuit?
Yes. Okay, Dean, so what's going on under the hood with diodes and MLVs? How are these things made?
So, TVS diodes, let's talk about those first. They're
Okay.
single-layer devices. These are based on a silicon wafer where the ESD strike is absorbed in the PN junction, which is the region in between the N section and the P section. The PN junction fully absorbs the ESD strike. And you'll see here as the strike comes in, the PN junction is flashing. That's where the strike's being absorbed. But it is a single layer device. PN junction is also directional, meaning that the current will flow in one direction but not in the other. So this is what makes it useful for protection of the circuits, in that it presents a very high resistance in one direction and a very low resistance in the opposite. However, many circuits require bidirectional protection, which means they must be protected on both the positive side and the negative side. To accomplish that, there must be a second PN junction in the circuit, and a little bit later we'll discuss that, but basically the PN junctions have to be connected in back-to-back configuration.
Okay, I got it. So what about the MLVs?
The MLVs are stacked layer devices very similar to multi-layer ceramic capacitors,
Okay.
except that the ceramic is made from zinc oxide, which is a semiconductor. That semiconductor is then doped with different materials like antimony that form nonlinear high-resistance barriers. Inside this ceramic structure is where the ESD strike is absorbed. The flashing region is the internal section of the multi-layer varistor, and it is completely absorbing the ESD strike. The ceramic itself is composed of millions of PN junctions. Millions of PN junctions that are bidirectional inside the ceramic layer, and that will break up the incoming strike into smaller packets that are more easily absorbed by the device.
Millions of PN junctions. Now, Dean, how does that work? How are these things built? And more importantly, what happens in various types of failures?
So let's talk about the bidirectional diode to start with. These would be the back-to-back diodes, and the first one I'm going to talk about is going to be the bidirectional diode that contains two dies. There's one die protecting the high side or positive side and a second die protecting the low side. Now, each of these dies have a single PN junction on the inside. So when you have an incoming ESD strike, what will happen is the strike will be absorbed within the PN junction. If the strike is greater than the current carrying capability of the PN junction, it'll short. With the fusing wire or the wire bond between the dies, can fuse open to make it into an open circuit. And this is what engineers in the past have talked about when they have open mode failures in diodes.
Okay.
So if the surge current coming through is less than the wire bond current capacity, no fusing will occur and the device will fail as a short circuit. This is something that most designers want to avoid, but diodes will fail as short circuits, in which case many engineers believe they only fail as open. So let's go to the bidirectional diode with one die but two PN junctions. In this case, I'm showing an SMA J33CA device, very common device used as protection as a TVS diode. On the inside, you'll see there's two lead wires, but there is a single die in between those two lead wires. So if we look at it under higher magnification, there's actually two PN junctions within that single die. So when you get a ESD strike coming in, it could come in from the high side, which would be next to PN junction 1, or from the low side on PN junction 2. The ESD strike coming in will short circuit or can punch through one of those PN junctions, in which case the device will fail as a short circuit. This type of device, unless it blows open, will not fail as an open mode failure.
Okay.
So in that way, MLVs and diodes are similar in that they both can fail as short circuits. So let's talk about what the MLVs look like. The MLVs, again, are multi-layer stack structures. They're bidirectional only. And on the screen, you'll see that there is a SEM, or a close-up of the internal structure, showing an electrode with the zinc grains and an electrode. The incoming strike will be absorbed within the ceramic. However, the structure of the MLV is multi-layer, so as the incoming strike hits the device, it'll be broken up among the electrodes, basically as a current divider. So that breaks up the strike into much smaller packets of energy that are easily absorbed by each of the layers. Now in this particular part, there's a total of 12 electrodes or 11 layers, so each layer takes only 9% of the incoming strike. This internal design is very important to the reliability of the multi-layer varistor. Total volume of the device, which would be the amount of ceramic between those electrode layers, is where the strike is absorbed. And that is very important also for the design of the part, depending on what the circuit requirements are. If the energy content of the incoming transient is greater than the energy rating of the MLV, in those cases we'll end up with most commonly high leakage, or in the extreme case, a short circuit. But again, what will happen as these transients tend to come in and hit the multi-layer varistors, leakage current will begin to increase.
Okay, so Dean, how are the power ratings changed for diodes and MLVs?
Again, going back to the diodes, being single-layer devices, so in order to increase the power rating or the energy handling capability, that PN junction being the critical part of the diode must be increased. Either the size of the die or the thickness of the PN junction must be increased in order to increase the energy rating. This will cause an increase in the die size, which will result in a much larger device. Bidirectional diodes with two internal dies, again, are limited to the max rating of an individual die. So if you have two dies in there, it doesn't double the energy capability of the part. It actually sets up each die on the high side and each die on the low side being equal to each other. The advantage of the PN junction technology in the diode is low cap. Now, with the low capacitance, there's a corresponding low clamping voltage, and I'll compare that against the MLV in the next section. Again, going back to multi-layer varistors, these are multi-layer devices. So in order to increase the energy rating, we simply add layers to the parts. Adding layers, though, does have a downside in some circuit designs where it'll increase the capacitance of the part while maintaining a size advantage over the diode. What this means is we can stack the layers vertically, increase energy rating of the device without having to physically increase the part size. The second advantage of this is that the higher capacitance can help in the broad spectrum EMI filtering, particularly on the power line applications. The downside is on signal conditioning, the higher cap can be a concern in that it may interfere with the signal transmission. The second downside is the difficulty in achieving very low cap values with an associated low clamping voltage. So in those cases, the diodes would have a little bit of an advantage on the capacitance.
Okay, so walk me through the comparison with regard to surges. Where does the energy go?
So to recap on the comparison, on the screen displayed or the different devices we just discussed, On the left side are the diodes, and what you'll notice immediately is that the diodes themselves are rather small. Most of it's packaging, it's lead wire, plastic. On the right-hand side, you have the multi-layer varistors, and what you can see with them is that as they are stacked, there's a much higher efficiency for surge absorption. In this case, the red areas are absorbing the incoming surges, so you can compare the diodes with the single PN junctions versus the total volume of the multi-layer varistors. So typically, the efficiency of the varistor is higher. It's greater than 70% of the component is used for ESD protection, whereas in a diode, you're looking at probably less than 5% of the component actively involved in suppression of the surge. This again will give a size advantage to the MLV.
Okay, and so what are the other differences in diodes and MLVs that we should be aware of?
So the VI curve, or the voltage current curve, is very important when considering whether to select an MLV or a diode.
Okay.
And there are important differences between the two. So on the left side, we have a typical MLV VI curve showing with voltage on the x-axis and current on the y-axis. And you'll see where the circle is shown that there is a very soft knee. As the voltage increases, the MLV will turn on, but it turns on with the soft knee sort of slow. The diodes, on the other hand, will clamp at a much lower voltage than the equivalent rated MLV. What this means is, for example, a 5.6 volt MLV will clamp for less than 18 volts or 16 volts typically, whereas a diode will be fully on at less than 10 volts.
Okay.
So the turn-on slope is much steeper for the diode without the MLV soft knee. So on the right side, there's a comparison curve being shown. In red, turn on of the diode starts at a much earlier voltage, and it rises very steeply, basically very close to 90 degrees vertically. And this becomes an advantage in that when you have to protect ICs that have low resistance to voltage surges or current surges, you want the diode to turn on and protect it quicker. Underneath the white circle on the red curve is where the diode turns on completely, and as you can see, the slope is very, very steep. The steep slope is very important for IC protection, particularly when the IC damage can occur close to the operating voltage of the device.
Okay, interesting. So, Dean, what else?
So the next consideration for the design engineers will be temperature derating of the circuit across the full operating range. This is important for proper operation of the circuit, and it's also important consideration whether to select a diode or an MLV. The diodes often require derating between 25 degrees C and peak operating temperature because they are silicon based. The peak power derating at max temperature can be more than 75% of the 25 degree centigrade peak power rating. This could force designers to use a much larger case size on the PCB layout than they originally intended. MLVs, on the other hand, require zero temperature derating across the full operating range. This often allows designers to substitute or replace their diode that they are using today with a much smaller component. In some cases, that can be reduced as much as 5-to-1 or even greater on the size reduction.
Okay, I think I see the difference pretty well, but how do I figure that into my application?
The MLV has two major advantages. It's a multi-layer structure and it has zero temperature derating.
Okay.
So both of these advantages combine for the highest surge handling per unit volume, which allows the designers to use a smaller device for the same application. And this is where the current circuits are heading. Everybody's looking for size reductions, and generally speaking, with size reductions will come cost reductions as well.
Sure.
Not only in the components, but also on the PCB circuit size, the connector size, other components, etc. So everyone's looking to gain these advantages. So the MLV does offer those two advantages that allow the designer to select a smaller component. So here's an example showing an MLV replacement for a diode. This is for 165 degrees C peak temp application. The existing PCB is too large for their next generation design.
Okay.
They're using a legacy diode, which is an SMA J33CA, which I showed on an earlier slide. Power rating of 400 watts at 25 degrees C, but at 125 it's less than 90 watts. This is a rather large device, 5.6 millimeters by 2.92 millimeters by 2.43. So it's basically a pretty big device. The designer then evaluated an AVX multi-layer varistor, and the part they evaluated was an 0805K size, and our numbering system is called a VCAS 080526C, which is equivalent to the SMA J33. The rating on the multi-layer varistor is 0.3 joules versus the 400 watts. places both of them very close to the same rating at room temperature. However, at the peak temperature of 125 degrees C, the multi-layer varistor is still rated at 0.3 joules. So it has the advantage of not changing between room temperature and peak temperature. So when you compare that and look on the PCB, as you can see now, the MLV in this application used just 20% of the prior design versus the SMA-J legacy design. So it allowed the designers to substantially reduce their circuit size.
Very cool. Okay, so Dean, when I choose a diode, for example.
So the diode major advantage, as we mentioned earlier, is a much lower VC, which is a clamping voltage, to the operating voltage ratio. Now, the circuit may restrict the design engineer on their choices as to how they protect the circuit and which device they select. So let's take another example. This one is also from the automotive industry, where the circuit requires less than 35-volt clamping to protect the IC, but the company policy or design policy requires at least an 18-volt rated part that goes on the battery line. As we all know, the automobile batteries are 12 volts, but many automotive companies require at least an 18-volt part on those battery lines. So the diode part number, which is typically an 18-volt rating, the clamping voltage will be less than 30 volts typical, which is very normal for diodes. So with an 18-volt circuit operating voltage rating, your clamp is going to be less than 30 volts. So it's a pretty low ratio. On the other hand, the MLV part, the auto grade 18-volt operating voltage part, will clamp at more than 37 volts. Again, very typical. Doesn't matter which supplier it is. It's hard to get an 18-volt auto grade MLV to clamp below 35 volts. And that's where the problem comes in. With the clamping more than 37 volts, it's greater than the 35 volts that is required by the circuit. So in this situation, the diode must be selected.
Okay, and I assume that even though we've been talking about differences, there are a lot of similarities in diodes and MLVs, right?
Yes, there are. Because diodes and MLVs are used in the same part of the circuit to protect the circuit from these incoming transients, they are used in many of the same applications. Consequently, the engineers are having to decide today between a diode or an MLV. As signal frequencies increase, the capacitance of the protection device becomes important. Diodes and MLVs both offer ultra-low cap products, which are typically less than 10 picofarads, in many cases less than 1 picofarad. Leakage current is also an important consideration, particularly in battery-powered portables. Diodes and MLVs both offer low leakage current products, which may be as low as less than 0.1 microamp or even lower. Furthermore, in some of the lines, they're using multi-line or array components such as an HDMI or even in CAN bus protection, where signal lines are very close on the PCB and space is limited. Again, diodes and MLVs will offer multi-line protection in a single component. In the automotive industry, there are some very significant energy test specifications, which are called automotive load dump tests. Those require performance under very harsh environments. Diodes and MLVs both offer products to meet the automotive load dump testing.
Okay, so are there any rules of thumb I can think about to help me guide through for my particular design?
Sure. Let's talk about some of these general selection rules. You want to select MLVs when you need stable performance across a full temperature range. You want to select the MLV when size reduction is important. You want to select the MLV when application is a harsh environment with a high level of repetitive strikes. Because of the multi-layer structure, they're able to withstand these type of severe environments without damage. You also want to select the MLV when higher capacitance is useful for broad spectrum EMI filtering. In this case, the MLV will perform both as a varistor and as a capacitor.
Okay.
So on the other hand, the engineer will want to select the diode when the circuit requires the lowest clamping voltage to working voltage ratio for the IC protection, as we discussed earlier in the case of the automotive circuit, requiring less than 35 volt protection, but they need a operating voltage of 18 volts and higher. Secondly, you want to select a diode when low cap is required, particularly less than 10 picofarads, plus low clamping. Again, less than 15 or 20 volts. In those cases, varistors will often have a much higher clamping voltage than the circuit can withstand. You also want to select a diode when the application energy requirement is greater than what's available in an MLV. This can happen in some of what they call the JSO load dump waveforms, which are prevalent in Asia. Some of those wave dump forms can be only handled by a power diode. Finally, you want to select a diode when a circuit requires unidirectional protection. And what this means is that the diode is a single die, protects in one direction. As we mentioned earlier, MLVs only come as bidirectional devices.
Okay, so what about reliability of these components? Anything we need to be aware of in that case?
This is a really key question, and this is one that I get often asked by engineers when I'm talking with them. Diodes have been in use for decades, so the reliability of the diodes, the designs of the diodes are very well known. For the multi-layer varistors, there is less history, less experience in designing with them. The best way to guarantee outstanding reliability starts up front by the selection of a top-tier supplier. The MLVs and diodes are used by billions in many harsh and demanding environments, such as even your car's engine control unit. Consider your Rolls-Royce Ghost that you park out in the South 40.
Okay.
Even it has computers and electronics that need protection. In fact, Rolls-Royce also uses both diodes and varistors on their electronic circuit boards. Or even that plane you take out Monday morning for your weekly jaunt across the country.
Okay.
Lots of avionics on board are using diodes and varistors as well for protection. When properly selected, MLVs and diodes will have outstanding reliability, typically in a parts per billion range, which satisfies most of the customer's requirements. Let me make one word of caution here. Using price and data sheets as the primary factors for your critical project can result in unexpected consequences. Now, we all know that cost is an important consideration. However, in many applications, the price of failure is much, much more severe than the cost of the component.
Absolutely.
So the number one selection factor should be a top-tier supplier. So here's a real-world example of not following the number one selection rule.
Okay.
In 2011, an AVX customer qualified an auto-grade varistor in a critical automotive application.
Okay.
Since day one, the AVX part had 0 failures, and it still runs with 0 failures. In 2014, this project moved to Asia, where the JV partner did a cost down and qualified a local supplier. The way they did the cost down was to do a datasheet comparison and found that the AVX and local source specs were identical. After doing a validation testing using the local source, typically small sample run, the local source was approved for mass production. Almost immediately, field complaints rose from 0 to around 1,500 parts per million. In 2015, AVX was asked to help in the investigation of why this failure began to happen. So the AVX analysis of the failures found the following. As you can see on the left side, the local source part had 5 layers in it. Each layer then means that on the incoming transient, and this part was used in a very active and rather severe environment, each layer absorbed 20% of the incoming strikes. As you can see in the picture, the internal ceramic was porous, and that was because the local source company used inferior materials. So over time and under repetitive strikes, those low number of layers, each one taking 20% of the incoming strike, failed to break up the transient into small enough packets to where the device can handle them. So it began to break down the internal structure, which eventually resulted in failure. So on the right-hand side, you'll see the AVX source part. It's a very big difference in appearance between that and the local source part. The electrodes are very strong. More importantly, the AVX source part has 11 layers in it. This means that each layer now only absorbs 9% of the incoming strike. Furthermore, the AVX part uses high-grade electronic materials. You can see the ceramic is very dense, the electrodes are very strong, which makes it much more robust against incoming transients. So under repetitive strikes, the high number of layers and the high quality materials breaks the incoming strike into small enough packets that does not damage the circuit or the component. Consequently, this part reliability was 0 failures in the field. However, it is more costly because of the extra number of layers.
All right, Dean, I think it's time for a recap. Can you give me your main points for me real quick?
Oh, I'd love to. Diodes are single layer, silicon wafer-based technology, while the multi-layer varistors are multi-layer zinc oxide ceramic-based. The MLVs offer substantial opportunity for both component and cost downsizing. Diodes offer much lower clamp voltage to working voltage ratios. Diodes require derating for operation above 25 degrees C, while multi-layer varistors is stable across the full temperature range. Both device types will perform at the highest levels of reliability when sourced from top-tier suppliers. So AVX offers both multi-layer varistors, which we call our TransGuard series, as well as diodes.
Excellent. Well, I think that's all I have time for today. Thank you so much for joining me, Dean.
Thank you for having me.
Before we go, you didn't forget to click that link, did you? There you can find out even more information about diodes or multi-layer varistors from AVX. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of eejournal.com or check out YouTube, keyword EE Journal.